Hi, guys. My name is Renaldas Zioma, and some of you know me as Ray. So we released Unity iPhone last year, and at the Unite, as you know. And this year was really great for us. We made a lot of new updates, and you made a lot of new great games. So I think you lived up to the challenge, and that makes us really happy. I actually started counting games which are made with Unity, which went to the App Store and which topped the charts. And so far, I managed to count 20 games. Pretty incredible lineup of games. And if you count the total number of games made with Unity iPhone, it's around from 7 to 10%, depends how you're counting, of those games actually are either in the top charts or were featured by Apple. It's a pretty high number of good games. Yep. And apparently, we helped a couple of people to make millionaires.
I'm not one of them.
So yeah, but the talk today is about the optimizations. And the first thing is, you already heard that, but I will tell that again. So especially if you're making the first game for the iPhone, your first game, then you should concentrate on making a good game first. And if it's your second game, then you still should be concentrating on making a good game first. And afterwards, you should profile it. Because, I mean, I noticed that many people just, of course, they're coming to the presentations, they come to forums, they learn a lot of stuff, and they kind of assume that there are some ways you need to do things. And those ways will make your games faster. But in reality, I mean, you need to know where are your bottlenecks, and you need to optimize your bottlenecks. If you start by doing some complicated things because you think they are suggested by other people, well, the problem is that it only makes your code more complicated. And then it makes, in turn, optimizing even harder. So you definitely need to, once you have a good game, then you need to start profiling it. And since we were working quite closely with several devs, some of those games you've seen on the tops, to help them profile and optimize, and to optimize our side of the game, of the code base as well. So we spent quite a lot of time profiling, and we've built, well, pretty decent tools inside the Unity runtime to help you profiling. So it's not the profiler you see in Unity 2.6. It's different stuff, but you need to use, you need to use iPhone profiler because that profiler will show you what's happening on the actual device. So how to start up that profiler? You just go to the app controller and you change the define from 0 to 1, enable internal profiler. And then once you run the game, you open the Xcode console, and you see the game, like every 30 frames, it will dump some information into this console window. And you need actually to learn how to understand this information in order to be able to optimize efficiently and find the bottlenecks. So that's actually what the internal profiler is spitting every 30 frames. So there's lots of numbers here, and I'll zoom a little bit into the first top part of it, which is the most important part. It gives you the overview. And the first thing you should know, it's all those numbers are in milliseconds. So if you're working on the performance, you should forget about the frames per second, FPS, or even the percentage is not that good. So why do you need to forget about the frames per second? Because, well, if your game is running 50 frames per second, and then you remove something, and it makes game run 30 frames per second, it doesn't really mean that the thing you removed is 20 frames per second slow. No. But within milliseconds, you can actually sum them up, and you can operate much easily with the milliseconds. So you need to kind of get used to them. So here on the top part, you see that it's, the first metric is CPU player. And that is actually how much time the Unity loop takes. That's the complete Unity loop. So for those 30 frames, it dumps minimum time, maximum time, and average time. Oh, logical. So, and at the bottom, the frame time, that is actually how much time it took frame to finish. So you could ask why the numbers, there's such a big difference between the CPU player time and the Unity time and the frame time. Well, that's because the iPhone is locked to the vertical sync. So you can't really render faster than the vertical sync. And vertical sync, that's 60 frames, 60 hertz. So if you can't render as fast as 60 hertz, then the next step will be 40 frames per second, and that's the frame. Oops, I'm pointing the wrong way. So the first question is, so how many milliseconds you need to plan your game? Well, you don't need to plan your game. When you're optimizing, you need to know what's your budget. And that's basically your budget. You just decide what frame rate you want to achieve, 30 frames. That's 33 milliseconds per frame, and 60 frames, that's 16 milliseconds. And once you know what you are targeting, you know your budget, then you should better learn what's inside Unity. And that's actually no one really, I haven't seen that many presentations where anyone's saying what's inside, what modules are inside Unity. And so I tried to cram them here. And actually, these names I put here, they exactly correspond to the names you see in the profiler. So, and these two columns here, that's Unity side. That's what we call CPU player in the profiler. And that's what's happening outside Unity. I will talk a little bit later about that. And what's inside? Inside, you see those two columns. And the first column, it says all game objects. And that means that those like kind of tasks will be executed for every game object you have in scene. So if you have coroutines, if you have some fixed updates, of course, that means that they need to be run for all game objects in your scene. The same, you can see that the physics will be running for all objects, no matter if you see them or not. The same goes to animation, skinning, and culling is actually the step which calls away objects you don't see. So in order to call them, you need to go through all objects first. And the second column is batching and rendering. And this part is executed only for those objects which are visible. So why do you need to know that? It's because, for example, if you see that your animations are taking too much time, then you know that it's probably because you have too many game objects in the scene which are animated. And if you see that the rendering takes too much time, that most probably related to not the whole amount of objects in your scene, but the amount of visible objects, which is logical. And then this third column, that's what happens outside Unity. That's OpenGL's driver when it copies the data, when it submits the data to the GPU. And the present buffers, that's where, because it has to flip between two buffers, it renders to one buffer, but shows another buffer. And the flip can actually take some time. We'll come to that later. Thank you. So, I'll go a little bit up. One more thing. All those things, well, we have only one CPU on the iPhone, right? So all these times, they're summing up. There's nothing here running in parallel. All of those on CPU, they run sequentially. So whatever times you see in the coroutines, animation, skinning, they all are summing up. So the second question, and I heard it many times, how many milliseconds, how do you know that some animation is slow? How much time should I expect from some tasks. And the answer, actually, there is no single answer. It highly depends on the game. And sometimes when sometimes you know, after working for a while, you know that when it takes too much time. So it boils down to experience to some extent. But in general, you should not be, especially if you're starting with optimizations, you shouldn't worry that much about that. You just need to keep in mind the frame budget. You have 33 milliseconds, and if everything fits, and it's OK. You don't worry about something being 10 or 12 milliseconds. If you see that something is going, you are out of your budget, then you should pick probably the highest number and try to do something with it. But in reality, everything depends on your game. So here, I just put all of those tasks. And like the bigger task, the more time it takes. So if your game is very physics, has a lot of physics and a lot of fixed updates, then of course, you need to plan and you need to think about that, and you need to reduce the time for the animations, for the skinning, the rendering. Everything else should be less complicated. So if you plan a game, or you have a game where there is lots of physics, then you need to know that you will have to sacrifice rendering for that. And if you have a different game where it's all about rendering, then it's OK to have maybe 15 milliseconds or maybe 20 milliseconds spent in rendering, but then you will have to have like zeros in other places, basically. Well, that's logical. There is no magic here. And the next part is usual suspects, usual things which usually in most games are slow. It's almost always just three things, either of them. So it's rendering, physics, and garbage collector. And I will talk about every one of them in details. So first, let's start with the garbage collector. And I hope you see what's that. That's a part of the internal profiler. I just took the part which is related to the mono and garbage collector. Mono, that's the part which runs scripts. And you can see, you need to understand this information. So here you see that the bottom part is mono memory. And that's the mono memory gives you information about the garbage collector. And the mono script, that gives you information about the scripts. So update, fixed update, and coroutines. Update, that's how much time all your updates take, and therefore. So if you see those numbers high, if they're high enough, then you just need to optimize your scripts, and there is a lot of information how to do that. But let's get I want to talk a little bit about the garbage collector. So there's like two numbers here, used heap and allocated heap. Allocated heap, that's how much memory the garbage collector took from the system. So that's the pool, and it will be putting your objects in that pool. And used heap, that's basically how much memory your objects are consuming. So the used heap will be always, of course, smaller than the allocated heap. And why collection happens? Well, it happens when the used heap is quite close, when the garbage collector has no more space in this big allocated pool for your new object. So, of course, it will have to go and do something, either expand, pool, or free it up. So collections, garbage collections, they happen only when you allocate something. If you don't allocate, like some people think that the garbage collector is running all the time. No, it's not running all the time. It only runs at the moment when you allocate something, and only at that moment when there is no more space in the pool. And when there is no space in the pool, the garbage collector will go and scan that memory, scan the all used heap, trying to find those objects which are dead, which has to be freed. And that takes time. So the last number is, you see here, it's a collection total duration. That means that during the last 30 frames, there was like max number of collection, one garbage collection pass, and it took almost 6 milliseconds to finish. And that number is proportional to these numbers here. Because it will have to go through all the memory. Like literally, it's going and looking for the objects and marking them up and then frame. So the more memory you allocate, the more time the garbage collector will take. So the next thing is, of course, if you want to, if you have the, no one likes those spikes. So what you need to do, you need to optimize your script code to allocate as less memory as possible. Ideally, you would not be allocating any memory during the gameplay. Of course, in reality, that's hard to achieve, and especially if you're using some third-party libraries or if you're using just C# libraries, because they like strings, stuff like that. All of them allocate memory. So if you're unlucky enough to have allocations going every frame or from time to time, then of course then you try to minimize those allocations. But if you're still allocating, then you have some control. You can actually call the garbage collector yourself. You can call it earlier than it would happen automatically. And why would you want to do that? For example, imagine you have a level, and then you're coming at some point, you're coming to the house and you're entering the house. And it doesn't really matter that at that point, if you would lose 10 milliseconds or 20 milliseconds, it would be a little bit less responsive for one frame game exactly at that moment when the character is entering the house. But it wouldn't ruin the experience for a player. It would be much worse if the character jumps in the middle of jumping and then the garbage collector runs. That would be much worse, probably. So if you know in your game that there are points when the interactivity is not that important for 1 or 2 frames, then you just call the garbage collector at that moment. And you can actually plan your levels. You can see how fast you're allocating memory. And then you can actually plan the level in this sense that, OK, in 10 minutes, I will have to garbage collect. So well, I will put like a house somewhere or some less enemies at that moment. Or another thing, for example, if the player pushes pause, then it's a good time to run garbage collector as well. OK, next is physics. And that's pretty easy, 3 points where you see the timing and information about the physics. And well, physics, it says how much time simulation takes. The fixed update says how much time your scripts are taking, those fixed update scripts. And the fixed update count, that says how many times, minimum and maximum, how many times the fixed update loop was invoked. So basically, the rendering, it just renders all the time, like as fast as it could. But the simulations, they need to be very precise. The steps should be always the same in the physics simulation. So we have a separate loop which runs at constant speed. And you set it up. And you need to actually, when you're optimizing, for example, physics, there is a lot of information out there. There were presentations about how to choose, what colliders should you choose, don't use meshes, blah, 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 blah. But one of the most important things is actually to set up correctly your time steps. If you set them up, if they are running too fast, then you're risking spending too much time in the physics. So you should actually increase the distance between those steps. You see this in the time manager. That's a fixed time step, and it's in seconds. So if you increase that number, then it will run physics less often. But then you can have problems like objects penetrating each other and gerunds being quite weird. Then you can actually choose the physics manager, and then you can increase the number of solver iterations. And that kind of doesn't make sense. Why do you want to have less fixed update steps, but at the same time more solver iterations? Well, that's just because the solver iterations are considerably cheaper than the whole loop. Well, so you balance them. You need to play around a little bit to get, if you're optimizing it, you need to play a little bit. And for example, if you can actually run physics slower than the rendering, but then you will have to choose interpolation method on the game objects. For example, the first Quake, it was running back then in I don't remember, in 96. But it was running actually at, the physics was run at 18 frames per second, if I remember correctly. And everything else was interpolated. Yeah. But we have a new thing in 1.5, which is not in the Unity 2.6 or whatever. That's, nah. It's maximum allowed time step. And that makes, that's a strange thing. For example, because the physics runs in those fixed steps, if your frame time becomes really bad, for example, if the garbage collector jumps up and you allocated like 4 megs of memory, and then it will take like maybe 60, 70 milliseconds just to run through that memory, and that's really bad, but you have this spike. But at the same time, because the garbage collector spiked, your physics will spike because it will have to do more iterations during those 60 or 70 milliseconds. And the next frame, it will be even slower. And then you have a huge spike for several frames. And to control that, you have new addition, which is maximum allowed time step, which does not allow, it stops physics from running more than n times, like more than 3 frames in this case, 3 frames per second in this case. So you can actually slightly reduce this number and see how it affects your game. Normally, it would not affect your game at all. But when it's spiky, then you will notice that the physics will be a little bit slower for some time, and it will be up again. But that will not, it will stop those bigger spikes from happening. Actually, a number of games are doing that. Usually, they clamp to like 10 frames per second, so the physics is not running more often than if your frame rate drops below 10 frames per second, the gameplay stops, like maybe becomes slower than, but it allows the CPU to catch up. Does it make sense? Okay, batching. So batching is an automatic way to reduce draw calls. And iPhone provides 2 ways to do that. And I will explain how they work from inside. All right. So dynamic batching, it will combine independent objects into a single draw call. And a good example, if you have falling crates, whatever, just arbitrary objects which are moving, and they will be automatically combined into one draw call. And the only thing it requires from your side, you need to share the same material for those objects. So that's how the loop looked in before 1.5. For every visible object, the renderer would go fetch that object, fetch the shader material, find the render, figure out the rendering states, set them, and then set the transformation matrix for that object, and then render that object. So for every object, basically, you have one draw call. In reality, you have even more if you have lighting and if you have multiple materials. So it's pretty bad. And in Unity iPhone 1.5, we do following. We first group objects by material. We sort them. Actually, any Unity, that is normal for Unity to sort non-transparent objects by material. So we sort them as well. And then we grab the object. And if we see that there is a number of objects in this group sharing the same material, then we will grab the object, and then we will transform it on the CPU. You've seen in the previous slide that it was sending the transformation matrix for every object. Because we can't do that, because we need to batch them. So we need to overcome that somehow. And the way to do that, instead of setting transformation matrix and allowing GPU to transform object, we're doing that manually on CPU. So we have like a big vertex buffer, and we transform the objects, and we're storing them temporarily. And then we set the material only once, and then we draw all this big vertex buffer once. So the draw call is expensive not on GPU side. It's expensive on CPU side. And vertex transformation, which we're doing manually, is as well on the CPU side, and it's expensive. Well, the one thing is that we implemented a hand-optimized assembly routines to transform them. And the iPhone has a pretty fast coprocessor, VFP. It's really fast. It's actually working faster than the GPU, and you will see later with the skinning. But still, it takes time to process. So we do that only on the objects which have some amount of vertices. So basically, batching some object makes sense only if that object will take less time to transform than actually to issue a draw call. So you've seen this 300 vertices at the moment, which is the cutoff limit. If the object is smaller than that, then it will be batched. If it's bigger than that, it won't be batched. And people were saying, so, well, that's unfair. If my object is 302 vertices, it's not being batched. But the point here is it's not about being fair with the objects, but the point is that we need to, you don't really want to batch those 302 bigger objects, because they will just take more time on the CPU side to transform than actually to draw it with the batch. And it doesn't make sense to cut your object in 2 or 3 parts in this case. So it just works for small objects. If you have lots of small objects like crates and just enemies, well, then it works. Next is static batching. And it will combine several objects into the single draw call. And the difference is, of course, the name says it, that the objects must be static. They can't move. And the example is, of course, walls and whatever. The wall geometry, basically, it never moves, or most of them. So that's a really good for static batching. And you need to do 2 things. The same as with dynamic batching, you need to use the same material for them. And the second thing you need to do, you need to mark it as static. It's in the inspector on the transform node, you put a small thingy there, it's static. And you never move it afterwards. And if you never move it, then it works as following. Not as following, but one small sidestep. The people were asking, so it's like a combined children's script. No, it's not. It's much better. And it's not like dynamic batching. It's different. It's different in the sense that it doesn't have this limit of 300 vertices. You can batch whatever size of objects. And it's much faster. So if you can use static batching, then you should prefer using static batching. So how static batching works, and that will answer the question why there is 2 nodes here. So the first thing, static batching will, in the editor, because you mark those objects in the editor, you say to Unity, I will not move that, then we can group them together at that moment, not at the runtime, but in the editor. And we do that only once. That's the props from the batching sample. You can download it from the Unity side. So it will, because Ethan went and put marked most of the objects as static, they are combined into one vertex buffer, just as it would happen with the combined children script. Except the combined children script generates a one object for you out of those. And static batching, it will still keep those objects as separate. It will create like a shared mesh. You don't see it, but internally it's creating a shared mesh. And those objects which are left in the scene, they're actually referencing that shared mesh. And we modified the code a little bit so it can, previously like object could only reference a complete mesh, but now object can reference like a subset of the mesh. That's basically how it works. So we create the single mesh, and then we patch those objects to point, instead of their own meshes, to point into this shared mesh and reference only part of it. At the runtime, that allows us to first do culling and find all the visible objects, unlike with the combined children, when this combined object is always visible. We can find those visible objects, and then we can batch them together. So how do we do that? We basically have a dynamic index buffer where we store the indices of only those objects which are visible. So we have a static vertex buffer which we created once in the editor, but we have a dynamic index buffer. And if you think about that, in case of dynamic batching, we had a dynamic vertex buffer, and that's way much more data to fill up. And with the static batching, because we have static vertex buffer but dynamic index buffer, we are filling up on the index buffer, and that's much less data to fill in. And that's why it's much faster on the CPU to do that. And we don't need to transform vertices or do anything because we did that already. We're only copying the indices. It's way faster. So once we generated this index buffer, we just set the material and draw the geometry the same way. OK. So the next question is how to batch. What do you need to do for batching? So it's obvious. I just repeat it. You need to have Atlas textures, because this way you can have a shared materials. You should be aware that you cannot modify properties per object. Although Unity allows you to write like render.material and then set some properties, it will actually create a copy of materials internally. And it's said in documentation, but sometimes you may miss that. So if you want to change the parameters of the shader, or material, you can do that only on a shared material. And in order to do that, you need to access it as a shared material. And the thing is that if you are using the shared material, then if you're changing some property, it will change, of course, for all objects. So you can't have, if you're using static batching or dynamic batching, you can't have one object changing color all the time. You need to have all the objects change the color. And you cannot change the UVs. Although it can seem like the placement of the texture is done per texture or some other way, it's actually per material. So if you are scrolling UVs, then it won't work. So if you have sprites and you want to animate them, instead of scrolling UVs, you should have different geometries. For example, if you have sprites, then animated sprite, you should have like 10 quads maybe, and then change them at the runtime. Do not change UVs. So let's take a look what breaks your batch. So of course, different material, as I said, that breaks the batch. Another thing is the transparency is breaking the batches. Because the solid geometry is sorted by material, but in order to render the transparent geometry, you have to sort it from front to back. And then for example, if you have two materials on your transparent objects, and once you sort them, you can end up with having object A, like farthest object having A material, next B material, A material, B material, so you can't batch them afterwards. You could, if they would be solid objects, then they would be sorted not by distance, but by material. So you have a group of A and a group of B. So if you have transparency, then you need, if you want to use batching, then you have to have the same material on all your transparent objects. If you're calling onRender, because in the onRender you can actually change even if you are not doing that, there is no really good way right now or fast way to determine that you change something. So in onRender you can change the property of the material, and that would screw up the visuals. You will get artifacts. So if the engine sees that you are using onRender for some object, it will turn off batching on those objects. Draw mesh. If you are drawing meshes through the draw mesh API, they actually are going internally through the different rendering loop, and that loop does not support batching. Next thing is layers. We can batch only inside the layer. So if you have multiple layers, only objects inside the layer will be batched, because it has to flush a lot of stuff between the layers. Not flush, but what? And there is two other things, those things you can have control. These two guys, you don't have control over them. So it's internally, of course, those index and vertex buffer have some limits. We allocate like, I don't remember exactly, around 4,000 vertices for the dynamic batching and something like that for the static batching. So if you have a lot of objects and then you're batching them, at some point, if there is no space, no space left in this vertex or index buffers, the batch will be broken. It's not bad, because if you have 4,000 vertices on the iPhone, that's pretty good. I mean, it's a good batch to render in one go. Probably you shouldn't be having too many those batches broken because of the vertex limits. And once this draw code is rendered, we're reusing the same vertex buffer again. And the next thing is internally, some geometry, mesh geometry, can be stored in strips or triangle lists. And you have no control over that. That depends on what way is better for GPU to store it. So if you have two separate objects, one object is stripped inside and another is triangle list, you can't, of course, batch them. So those two things you can't control. And some people are saying, so I counted that it should be 10 draw calls, but I'm getting 12 draw calls. What's wrong? Well, nothing wrong. It's probably something like that. But you shouldn't be, I mean, just don't worry about that. Unless it's a really bottleneck for you. Like you have, I don't know, if that's a bottleneck, then you should think about restructuring your maybe data, maybe optimizing your content. Unless it's a bottleneck, just don't worry about that at all. And draw calls in the editor, we modified a little bit the statistics window, and now it shows emulated draw calls and batch draw calls. And it's only rough approximation. The editor it's OpenGL. It's not OpenGL, so it's running on a different, the code there is slightly different. So it doesn't do any batching. It just pretends to do batching. So it can't be exact. So if you see difference, no, that's normal. It's just for you just to get the big picture, just to understand. Okay, if things are batching at all, or they are not batching completely. So you just need that for this thing. It's not to predict exact numbers. And again, the exact number, if it's 12 draw calls or if it's 15 draw calls, it's not that big difference. Most probably there are other things where you can optimize stuff. And again, share materials. Even if you don't, even if you can batch, even if Unity can't batch things for some reasons, you should use same materials as much as possible, because there's a lot of optimizations made inside now, which helps if Unity comes and sees that, oh, that's the same material I used previously, and it doesn't need to do a lot of stuff, it just can proceed. And that saves a lot of time. So even if everything else fails, you still should use texture atlases and share as much materials as possible.
So Renaldas asked me to just show a couple of quick examples from TouchKO to illustrate how we took advantage of some of these features and I guess potentially translate it into artist talk, something like that. So for anybody who saw my and Matt's talk yesterday, we kind of gone over a little bit of this briefly, but the stats window here, you can see in the game view is more or less, it's pretty close to what we're getting on the actual device. So if I just hit play here, we've got some stuff with these effects at the beginning, but during an actual round, we're somewhere here in the low 20s on draw calls. And you can see the number of editor draw calls is more around 40, so we're taking advantage of the static batching for all the crowd back here, all of the environment in the background. And if you saw those word graphs that he put up, we're kind of more in that second category where we have virtually no physics happening at any given time. Most of our time was spent on rendering because we have larger textures, higher vertex counts, things like that. But like he said, basically the way the static batching works is that it's a heck of a lot better than just a standard combined mesh, because if, for example, I combine this little piece over on the left here with this piece over on the right here, but my view frustum looks something like this, the bounding box for that combined mesh is still inside my view frustum, and so all of those vertices, even though I'm not actually rendering them, are still sent to the GPU. It's just kind of a big waste of your time. So the nice thing is if you cut up your environment like this, it's just going to use the bounding box of each of these individual sections to determine, like Renaldas said, which of these gets sent to the GPU. And so kind of the artist definition of this, I guess, from my standpoint is that basically dynamic batching has to send all of the vertex data because all the objects are being transformed. So that's things like the position of the vertex, the normal, and so on. And that's just a ton of data. But like Renaldas said, when you're using static batching, all of that stuff, since the objects don't move, basically gets done, it's stored up front. And so all you have to check after the fact is just the vertex index, or the little sub-object index. And also, like he said, you can't do batching on objects that have animated UVs. And so these crowd people here, for example, we had originally been putting the UV scroller object on each of these. And what happens is just because of little floating point imprecisions and so forth, they can end up like hundredths of a unit off from one another. And so Unity then says, well, these are different materials with slightly different properties. And so what we did was the shared material approach, where we're just animating the UV offset in the shared material so we can take advantage of static batching even in things that are animated. So there isn't really a hard and fast rule about this. And obviously keep in mind when you're creating your content that your vertex counts here in a program like Maya are not exactly what they're going to be on the device, because you're going to have degenerate triangles, you're going to have additional vertices because of your degenerates anywhere that you have UV separations or normal separations or anything like that. But just basic things that you can do, like Joachim had mentioned on Tuesday, I think. I did a lot of the really anal UV layouts where I basically have some object that, if I want a tile or whatever, I make sure that I don't have any seams on it by just kind of flipping it back over itself multiple times, so it's all just unwrapped in space. And you can see our Atlas texture for this. It's relatively small. I think in game, this gets knocked down to like a 256 or something. And then we have a larger light map here for all of the components that are sharing that same material, and that just sort of helps add variation and detail and so forth. So the other thing that Renaldas is going to talk about in a minute, and so I'm just going to kind of briefly touch on, is taking advantage of the new skinning in Unity 1.5. So something that Unity 1.5 added apart from a lot of other just general optimizations was the skinning, like he said, is now done using the VFP coprocessor. So it's all kind of done in assembly, and it's incredibly fast. It's faster than the GPU. So there are some specific skinning paths that take advantage of this optimization. He'll talk more about what those are. But if we look at like a character that we have in the game here is composed of a few different meshes. And part of the reason for this is because we swap out body parts in the game, and these have different materials and so forth. But the characters have a low-res body here, which is something around like 2,000, 2,500 triangles, I think, on the actual device. And then we swap in a high-res mesh for the close-ups. And basically, you just want to keep in mind that you don't want to add any joints to your, or any bones, rather, to your bind pose that aren't actually influencing the object. And so if we look at the trunks here, and I say, look at, we've only got 4 bones here that are affecting the trunks. It's just the pelvis, the first spine bone, and then the 2 hips. And so that's a way to get some cost savings. And then, of course, in the Unity side, you have to make sure that you set it up correctly. So there are quality settings for skin mesh renderers. If we take a look at this guy, you can see he has all these different skin mesh renderers as part of his character here. And the high-res one, which is for the close-ups, like when we have a slow-mo replay and his face is all jiggly, we wanted to have 4 influences per vertex. And that's just because we want to preserve a lot of the fidelity and the facial deformation and the shoulders and things like that. But the low-res characters are actually only using 2 bones per vertex. And some of these other smaller objects are also using 2 or 1, just to make sure that we are getting as much cost savings as possible on character skinning. So I guess you want to talk about how that works?
Yeah, well, so basically, as I said, the iPhone has a very fast VFP core processor. It's comparable with how SEC works, kind of just takes a vector and several floats and does the operations on them at the same time. So it's really good for things like transformation and skinning. And our current implementation of the skinning, we wrote several paths, so it depends on how many bones, how many weights per vertex you have. But one of the fastest paths, they can do around 3.5 million vertices per second on the 2nd generation device, and it's way much faster than the GPU is doing skinning, and it's actually way much faster than the GPU can render them, even if they're not skinned. So the GPU can render like around 1 million vertices. So, but still, we're actually bound by memory. We're not bound by the computations. So just great. But here I put like small tables where you can see which paths are optimized actually. If you're not on that path, then you will go through the generic skinning, and that's way slower. So you should think about what paths you're using, and basically that's the 3 combination, the 1 bone, 2 and 4 bones. That's the quality of the skin you set on in Unity. And as you see, for the 1 bone, for one weight vertices, meshes with 1 bone, whatever, it's called rigid skinning. So if you have 1 texture and the mesh is lit, then it's a fast path. Those stars mean fast path. In other ways, it's taking the generic. So I kind of figured out that if you are using the rigid skinning, then most probably you are quite low on the performance, and you don't want to use 2 textures at all, and probably you're not interested in unlit at all. In case of the 2 bones, all paths are actually implemented. So because that's one of the most used, and I think that's the default setting, and therefore we put all 4 paths implemented. So it's actually like a 1 separate routine to do every path. So it's specially optimized for that, depending on the size of the vertices and stuff like that. So it's kind of optimized for these cases. And in case of the 4, it's actually the TouchKO guys asked us to implement 2 textures. support for the full bone because they are used. I think you are having like a
right. We have a second UV set on the characters for their tattoos. So the skin texture is actually just symmetrical; it's mirrored. And then the second UV set has support for asymmetrical, so we can have a big dragon tattoo on their back or something like that.
And well, generally this path is fastest. But it's not like there is a that path is approximately 40% slower. So it's okay to use two bone weights without big problems. Hello? Oops. So, and next is just, I will go pretty fast over the profiler, showing you if you have problems with these numbers, like don't look at the numbers right now, but just keep them in mind. If you see those numbers high up, if you think that they're too high for your application, then that's the steps you should do. So if you CPU open GOS driver means that that's what driver is doing. So if those numbers are too high, then you should reduce vertex counts. You should use single texture instead because it will reduce the size of the vertex, and turn off lighting. That helps. If you see high numbers in the render on the batching, then that means that you should share more materials. You should improve your batching. Otherwise, you should just remove objects from the scene. Culling. Well, if the color is, usually you shouldn't see high values there. Usually it should be less than 2 milliseconds. If it goes up higher than that, probably you have a lot of objects in the scene. So you should start removing objects from the scene. Or you can do, if you have like a side scroller, for example, then you can deactivate parts of the scene up front. Like you only activate some area which is around the camera, so the color will go only and touch those objects which are activated. So you have to write like a manager which activates parts of the scene as you go and deactivates the back. Skinning, if the skinning is high, then you should lower the skinning quality, going from 2 bones to 1 bone, and reduce the vertex counts on your skinned meshes. It's easy. Animation. Well, that means removing bones, removing objects which are animated, and yeah, you can reduce number of, if you have simultaneously running lots of animations, then you should optimize that. Just remove them. You don't need them. So in physics, there is a lot of information about how to optimize physics, so I'm not going into the details. But if you see, if you see that number, the physics fixed update count high, like 10 or something, then you need to tweak your maximum allowed time step value. That means that you have spikes, and the physics is running too many iterations during those spikes. You should cap that. That's the easy one, and just optimizing your scripts. Only one item. And if you see this number high, usually you should look at the average number, though, not at the maximum. But at the average, if it's more than 6 or 7 minutes, it's just random number. You need to figure it out yourself. But if that number goes high, like 10 milliseconds and 20 milliseconds, most probably that means that you are not CPU bound, but GPU bound. Because at the CPU present, when it flips the buffers, if the GPU is lagging behind CPU a lot, then the CPU will stop and wait until the GPU finishes the work. And that's where the CPU present time comes from. It will always be a couple of milliseconds. I have no idea why, actually. It just probably driver does something there. I'm not sure. But just if it goes higher than that, if it's like 10 milliseconds, that most probably means you are GPU bound. Then usual steps. You should not minimize your alpha tested surfaces. Then if you have alpha blending, then you should reduce that. Simplify your shaders. Instead of having 2 textures, use 1 texture. Turn off lighting if you can. Use less lights. Pre-bake lighting, do whatever you want, just to simplify your shaders. And then simplify your geometry. So it's easy steps to make your game run faster. And here I want to show you something just for fun. Because the next step will be questions and answers, and you have 1 minute to think about your questions while watching. In case if you haven't seen that. It's on YouTube. I mean, we found it a couple of months ago, probably, on the YouTube. So someone who made the Portal clone, which is pretty cool. There's actually one more, which is made by Touch Arcade. Yeah. But basically, now it's the questions and answers. Oh, you want to watch it? It's a little bit buggy, but still cool. I didn't thought myself that it could be possible, but yeah. Okay, do you have any questions? No. So the question is, there's a mic somewhere here, I think. Whatever. The question was how much heap space the coroutines take. I actually don't know. Joachim, do you know?
What exactly? Starting it or
Starting.
I don't exactly know, but I mean, starting a coroutine definitely has some overhead. So if you're starting a lot of coroutines every frame, then and you want to not take any garbage collector hit on it, then don't do it.
Or do it at least, I don't know, maybe once if possible. Actually, there is one trick with the garbage collector that if you, for example, if you know that you will be allocating a lot of memory anyway, and first it will like always increase the pool. So for first like minute or something, it will be always increasing the pool, and you don't want to have these spikes all the time. So you can actually go and pre-allocate, like ask Mono to allocate you big arrays to pre-allocate 2 megs or something. Then you will be getting, of course, garbage collector corrections. But the point here is that during the first minute or so of the gameplay, you won't have like spikes all the time. No more questions? Yeah.
How would you do that oval effect without red detections?
I don't know. I didn't do that. You can find it on the YouTube, and you can try asking people who did that. Maybe they answer you. I don't know. But there is no render detection. We didn't. It's not that we gave a render detection to someone. Yeah, I don't know. Yep.
Render detection is going to come in Unity iPhone at that point?
Yes. Yes. Especially with the OpenGOS 2.0 support. Well, we plan to release it with the OpenGOS 2.0 support.
What was the question?
If we're gonna release, when the render target support will be on the iPhone, if ever. Yes?
Are you sure you didn't give him render text?
No. No. No.
When?
When?
Is that word in the Unity vocabulary?
No, we don't use this word. Well, as soon as it's done. I mean, if you are really interested, you should be applying to beta program. Then most probably you will get it earlier than everyone else. But then you will have to test it and. Yeah. But why do you? How would you actually use the 2.0? Why it's important for you?
Well, 2.0 introduces shaders, and so doing more sophisticated things. A little bit harder, very sophisticated. There's things that maybe physics.
For physics, that's
There's like a huge number of arbitrary things that you can do.
Yeah, I understand, but the practice is that the device is, I mean, it's much faster than the 3G, but it's not that much fast that you will go crazy with the shaders. That's one thing. And then the next thing is that we expose for 8 textures already for the 3GS. So you can have much more complicated shaders if you are targeting 3GS. So you would still be using fixed function, but you can layer up to 8 textures.
Well, there's also, like, when you it's 2.0, then you can intermix, like, so when there's actual 2.0 support,
Yeah.
You can intermix with, let's say, native rendering or things that are going on that you're actually using, let's say, like right now I'm intermixing with OpenGL 2.0 and the existing Unity 1.0 or 1.5, right?
Yeah.
Or OpenGL, yeah. And so 2 OpenGL contexts actually have to be created. One that supports 2.0, one that supports 1.5, and then.
Yeah, I understand. So you would use, you want natively to use OpenGL 2.0. No.
Yeah.
Okay, I see. Actually, well, with the OpenGL 2.0, I can say that the biggest challenge for us is the fixed function support, because we need to support it. Like we could release.
That can be wrapped, right?
Well, we need to generate them on the fly.
Yeah.
And there is, when you start thinking about that, even if you play the games with the, if you're playing 3GS and you are using OpenGL 1.1,
Yeah.
then sometimes you see stuttering. That's because it's actually simulating the fixed function and it's generating shaders on the runtime. But that's inside the driver, and it's quite optimized. We will not be able to go that low, and most probably that will mean that our spikes will even be bigger.
Okay.
So you will, when the OpenGL 2.0 comes, most probably you would like to write shaders all the time, not using fixed function, because the fixed function will be kind of not slower, but it can introduce this like spikes sometimes. Thank you.